In section 8.2, we look at the trigonometric form for complex numbers. First, let's talk about graphing complex numbers. The graph of a complex number a plus bi is a vector that extends from the origin out to the point AB. To understand this, let's take a look at an example. Here we want to graph each of the following complex numbers. We have the number 2 plus 4i. So to graph 2 plus 4i, we're going to go to the point 2, 4 in the coordinate plane. So 2, 4 is right here. And technically, a complex number is just that point. But the way this book describes it is a vector from 0, 0 to that point. So this is the complex number 2 plus 4i. The next one is negative 2 minus 4i. So to graph that one, I'm just going to go to the point negative 2, negative 4, which is down here. And I'll extend a vector in that direction. And finally, we have 2 minus 4i, and to graph that one, I will go to the point 2, negative 4, which is down here, and I'll extend a vector in that direction. So graphing complex numbers is nothing more than graphing a vector, but I have to be completely honest here. A complex number is actually just the point in the plane. However, drawing the vector is going to help us understand the complex number a little bit better. In our next example, we want to graph the complex numbers 1, I, negative 1, and negative I. So let's remember that the number 1 is the same as 1 plus 0i. So to graph this, we are going to go to the point 1, 0, which is right here. So this is the complex number 1. And again, you don't have to draw the arrow here, but I will just because this is the way the book is describing it. The next complex number they want us to graph is the number I. We know that I is 0 plus 1i, so that will be the same as graphing the point 0, 1, which is right here. So that is the complex number I, and then we can go ahead and draw the vector. And then next we have the complex number negative 1, which is the same as negative 1 plus 0i. And so to graph this, we will graph the point negative 1, 0, and draw the vector. And so this is the complex number negative 1. And then finally we have the complex number negative I. And negative I is the same as 0 minus 1i. And so to graph it, we would graph the point 0, negative 1, which is here, and draw the vector. So these are kind of special complex numbers. And I want you to notice that, the numbers 1 and negative 1 are real numbers, and those are always on this line. And the numbers I and negative I are imaginary numbers, and those are always on this line. So for that reason, the x-axis is usually referred to as the real axis, and the y-axis is usually referred to as the imaginary axis. So any number that is a pure real number will always be on this line, and any number that is a pure imaginary number will be on this line. And then if we have a number that has a non-zero real part and a non-zero imaginary part, those numbers will always occur in one of the quadrants. Now let's begin our discussion about the trigonometric form for complex numbers. So first we'll start with the definition of the absolute value or the modulus of a complex number. So if we have a complex number z equals a plus bi, the absolute value or modulus of that complex number is the distance from the origin to the point AB. And if this distance is denoted by r, then this distance is r equals absolute value of z, which is the same as absolute value of a plus bi, which is the square root of a squared plus b squared. Now, before I do the example below, let's talk a little bit about why this is the case. So in general, if I have a complex number z equals a plus bi, we know that this number is the number that extends from the origin out to the point AB. All right, so this is the number a plus bi. And you should notice that you can make a triangle here. And in this triangle, this would be a and this would be b. And we're defining this modulus, or this absolute value, to be the letter r, and it is the distance from the origin out to this point. And so we know that r is right here. And so from this picture, of course, you know a squared plus b squared must be equal to r squared. And if you take the square root of both sides, you get r is equal to the square root of a squared plus b squared. So we can see very easily the justification for this. It is just the Pythagorean theorem. Now, what you need to get familiar with is the fact that you can talk about the absolute value of a complex number, or you could talk about the modulus of a complex number. These are the same thing. Now, I will mostly use the word modulus, but we could also say absolute value. Okay, now let's go ahead and do this example. So we want to find the modulus of each of the following complex numbers. So the first one here is the number 5i. So we want to find the absolute value of 5i. Let's keep in mind that this is the absolute value of 0 plus 5i. And you can see now that you have a equals 0 and b equals 5. And so this is just the square root of 0 squared plus 5 squared, which is the square root of 25, which is 5. So notice that there is no need to graph the complex number in order to find its modulus. The next one, we want to find the modulus of the complex number 7. Well, this is kind of interesting, isn't it? Because you all know the absolute value of 7 is 7. But let's go ahead and use the definition that we have here. So 7 is the complex number 7 plus 0i. And using the formula for modulus, this would be the square root of 7 squared plus 0 squared, which is the square root of 49, which indeed is 7. So notice that the definition for absolute value of a complex number is the same as the definition for the absolute value of a real number. And finally, we have the number 3 plus 4i. So the modulus of 3 plus 4i is just the square root of 3 squared plus 4 squared. This is the square root of 9 plus 16, which is the square root of 25, which is 5. So finding the modulus is a relatively straightforward thing to do. Now let's give the definition of the argument of a complex number. The argument of a complex number z equals x plus y times I is the smallest positive angle theta from the positive real axis to the graph of the complex number. So if you have your complex number drawn in the graph here, the argument of the complex number is nothing more than this angle theta that we have to rotate through to get to that complex number. And we always want to express this angle as a positive number. And now we get to the definition of a complex number in trigonometric form. So the definition says the following. If z equals x plus y times I is a complex number in standard form, then the trigonometric form for this complex number z is given by the following. Z equals r times the cosine of theta plus I times sine of theta, where r is the modulus that we talked about a minute ago, and theta is the argument that we talked about. Now, let's see why this is true. So if you look at the graph of your complex number, you'll notice that you have a right triangle here. And we know from trigonometry that the cosine of theta is equal to x divided by r, and the sine of theta is equal to y divided by r. And if you solve for x, you get x equals r times the cosine of theta. And if you solve for y, you get y equals r times the sine of theta. So if we have a complex number z equals x plus y times I, notice that we can replace x with r cosine of theta, and we can replace y with r sine of theta. And if we make those replacements, we get z equals r times cosine of theta plus r times sine of theta multiplied by I. And then, of course, what you can do here is you can factor out the r, and then what you have left is cosine of theta plus sine of theta times I, but what we like to do here is put the I in front of the sine of theta. So if you know the argument of a complex number and its modulus, you can easily write that number in trigonometric form. And it turns out that this representation for a complex number is extremely useful. So in this example, we want to take the complex number z equals -1 plus I, and we want to write it in trigonometric form. So right now we have the standard form for the complex number z equals -1 plus I, and we want to write it in trig form, which of course is z equals r times cosine theta plus I sine of theta. So what we need to do is we need to figure out what is r and what is theta. So what I'm going to do first is graph the complex number to help us see what is happening here. So the complex number -1 plus I, let's remember that this is -1 plus 1I. So I'm going to go to -1 on the real axis, and I'm going to go to positive I on the imaginary axis. And I'll put a point there. This is the number -1 plus I. And then just to help us see things a little bit more clearly, let's go ahead and draw the vector for this complex number. So I need to figure out how long that vector is. That'll be our modulus r. And then we also need to figure out the angle theta right here. So what I like to do is go ahead and make a right triangle here. You know that this distance is 1 and this distance is 1, right? And so we can find the modulus r by simply taking the square root of -1 squared plus 1 squared. So what I'm doing here is I'm using the real part and the imaginary part. And please note that it doesn't matter if you use positive or negative values here, because since you're squaring them, it comes out to be the same. So when I talk about this triangle, this distance here is 1, but I mean technically that corresponds to the number -1 on the real axis. Anyway, this is equal to the square root of 2, so we have our modulus. Now we need to find theta. Well, if you look at the triangle, you'll notice that you have 1 here and 1 here. That means that this angle right here must be 45 degrees, and that means that our angle theta is 135 degrees. So now we have our modulus r and our argument theta, and now we can write this complex number in trigonometric form. We can say that it is equal to the square root of 2 times the cosine of 135 degrees plus I times the sine of 135 degrees. So this is one way to represent it. Or you could also write it in radians. So that would be radical 2 cosine of 3 pi over 4 plus I sine of 3 pi over 4, because 135 degrees is the same as 3 pi over 4. You can write the answer either way. Normally we use degrees, but we should be comfortable with degrees and also radians. In this next example, we want to write the number 4 take away 4i radical 3 in trigonometric form. So it's pretty much the same thing. Notice that our complex number here is z equals 4 minus 4i radical 3. So this is the same as 4 minus 4 radical 3 times I. So our real part is 4. Our imaginary part is 4 radical 3. Now to graph this, you could approximate 4 radical 3 on a calculator, which is about 6.9. And so when I graph this, I'm going to go to 4 on the real axis and negative 6.9 on the imaginary axis, which is down about here. And so this complex number, if I graph it, would be right about here. And then I'll go ahead and draw the vector. And what I can do here is I can make a right triangle that lines up with this. We know that this is 4. We know this is negative 4 radical 3. You should recognize that this is a 30, 60, 90 triangle because one of your legs is radical 3 times the other leg. So we can recognize that this angle here is 60 degrees. Also, we know the hypotenuse is twice as big as the short leg here, so the hypotenuse has to be 8. And if you recognize that, then you know the modulus is 8, and you know the argument is this angle here, which is 300 degrees. Now, if you don't see that right away, you can always find your modulus R by taking the square root of the real part squared plus the imaginary part squared. And if you do the math on this, you get the square root of 16 plus 48, and that is the square root of 64, which of course is 8. And then to find the angle 60 degrees here, you could always find the reference angle by taking the inverse tangent of 4 radical 3 over 4. And if you do this on a calculator, you'll find that this is equal to 60 degrees. So that's in case you don't recognize it. But if you recognize that you have a 30, 60, 90 triangle, it does make this a lot easier. And so now I can write the complex number in trigonometric form as r times cosine of theta plus I times the sine of theta. So it's 8 times the cosine of 300 degrees plus I times the sine of 300 degrees. In our next example, we're just going to do the opposite. We're going to take a complex number in trigonometric form and write it in standard form. And for this, you don't have to do a graph, although you can draw a graph if you like. So if I try to make a graph here, notice that we have r equals 2, so that's the modulus, and the argument is 60 degrees. So if I draw something that is at 60 degrees and has a length of 2, it will look something like this. And so since we have a 30, 60, 90 triangle here, we know that this side will be half of the hypotenuse and this other side will be radical 3 times that short leg. And from there, we can see that z is equal to 1 plus I radical 3, right? Because there's our real part and there's our imaginary part. So you can use a graph to do this, but you don't actually have to use a graph. You could simply multiply it out. So if I have 2 times cosine of 60 plus I times sine of 60, we could just compute these values. We know the cosine of 60 is 1/2, and we know that the sine of 60 is radical 3 over 2. And then when I distribute the 2 to each of these, it's going to cancel the denominator, and we are going to get 1 plus I radical 3. Same thing. So converting from trig form into standard form is relatively simple. For our final example, we want to use our calculator to write the complex number 20 times cosine 105 degrees plus I sine of 105 degrees in standard form and round the numbers to the nearest hundredth. So if our complex number is this one, all we have to do here is distribute the 20, and this will be 20 times the cosine of 105 degrees plus 20 times the sine of 105 degrees times I. And now we just need to plug this into a calculator. So if you plug 20 times the cosine of 105 degrees into your calculator, you get negative 5.18. And if you plug 20 times the sine of 105 into your calculator, you get 19.32. So rounded to the nearest hundredths place, this complex number in standard form would be negative 5.18 plus 19.32 times I.